Hello, I'm Savannah Garmon, and this is my virtual talk for the canceled APS March Meeting 2020. So my title is the Anomalous Exceptional Point and Non-Markovian Purcell Effect at Threshold in 1D Continuum Systems. So we start with a definition. So an exceptional point is a branch point in the parameter space of a given non-Hermitian Hamiltonian at which two or more eigenstates coalesce. So a key property is that the usual diagonalization scheme of the Hamiltonian breaks down at the exceptional point. So if there are two coalescing eigenstates, we would generally expect there to appear a 2x2 Jordan block in the reduced Hamiltonian. A further key point is that the eigenvalues can be expanded in the characteristic Puiseux expansion in the vicinity of the exceptional points. So this Puiseux series, it looks like a Taylor series, but there are these fractional exponents. And then we see the exceptional point, epsilon EP bar. It's literally a branch point in the parameter space. So then a further point is that an exceptional point at which n eigenstates coalesce, we would generally expect then there would be an n by n Jordan block in the reduced Hamiltonian. And the Puiseux series would give rise to a 1 over n power. And so then this is generally referred to as an EPN in the literature. But in this case, we'll study an anomalous exceptional point, which looks a little bit different because so the Puiseux expansion will have a cubic root of G here, where G is the coupling in the Hamiltonian. I'll introduce in a moment. However, the reduced Hamiltonian actually just contains a 2x2 Jordan block plus an additional state which is just degenerate in the traditional sense. Further point is that the anomalous exceptional point results in an unusual power law decay that we'll see towards the end of the talk. So now I claim that this anomalous exceptional point is a rather generic effect in 1D continuum systems. But as a simple example, prototype model, I use this simple tight binding chain here with a side-coupled quantum dot or quantum emitter. So for our Hamiltonian, the adjustable parameters in the model are G, the coupling to the dot, as well as epsilon D, the potential on the dot. Now we can easily diagonalize the tight binding portion of the model by introducing this simple Fourier transform. Doing so, we can obtain the partially diagonalized Hamiltonian, which epsilon k here is the usual tight binding dispersion, which forms a conduction band that extends from -2 to +2 after we set j equal to 1. And we note that this has the usual 1D Van Hove singularities at either edge, -2 or +2. Then the discrete spectrum from this model can be obtained from the poles of the Green's function, in which here sigma z is the usual self-energy function, which for this simple model can be analytically obtained in this form. And then the dispersion equation for the discrete eigenvalues takes this form, in which here in the self-energy, we notice that the Van Hove singularities that I mentioned previously appear in the denominator. Now, the discrete solutions for this model can be organized into the complex energy plane, which for this model is two-sheeted, in which the branch cut here is given by the tight binding dispersion that I showed earlier, which connects the two Riemann sheets. In the first sheet, there reside the bound states, which for this model, there is exactly two, one residing directly below and one residing directly above the continuum. In sheet 2, there reside any other states, including resonant states, which would have a complex eigenvalue in general. Now we introduce a simple categorization scheme for the simplest case of the exceptional points. That is the EP2s, which are the most commonly studied in the literature. So a type A, or an EP2A, is the case in which two real eigenvalues coalesce before forming a resonance-anti-resonance pair. Then the EP2B is the case in which two pre-existing resonances coalesce before forming two different resonances. Then the main subject of this talk will be an anomalous exceptional point, which involves the coalescence of a resonance, anti-resonance, and bound state that converge directly on the continuum threshold. Now we look at the discrete spectrum for this model, which is the solutions to the dispersion equation I showed earlier, which here we are plotting the real part and the imaginary part of the solutions to this equation as a function of the parameter epsilon d in the vicinity of the lower threshold at -2. Now we notice that a little below the lower threshold, we have a real valued ordinary EP2A, at which the two virtual bound states coalesce before forming the resonance anti-resonance pair. We notice that the decay width, the imaginary part of the resonance eigenvalue, we notice that it's enhanced in the vicinity of the threshold here. Then moving to the main point of the talk, at the case epsilon d equals -2, we are directly at this lower threshold. And then in this case, these two, the resonance, anti-resonance, and the bound state, we can easily show they converge if we choose epsilon d -2. And as g vanishes in this expression, we easily see that there must be these three states, these three eigenvalues converging on -2. So that's the mentioned anti-resonance, resonance, and bound state. And we can obtain the Puiseux expansion for the eigenvalues in this vicinity, which have the form that we mentioned earlier, which is the cubic root in terms of G, the coupling. Now, a point is, as we mentioned previously, the resonance decay width is enhanced near this anomalous exceptional point. In particular, it has this G 4/3 character, which is enhanced relative to the usual Fermi golden rule case. And the influence of this on the local density of states and other quantities is studied in these papers. However, instinctively, one might expect that the enhanced decay rate would result in enhanced exponential decay, for example, in the survival probability of the initially occupied quantum dot state. However, that fails to take into account the fact that near the threshold, we would also expect the non-Markovian dynamics associated with the branch point effect to be enhanced. So to evaluate that question more precisely, we then look at the survival probability, which is written as the square modulus of the survival amplitude, which can be written in the form given here, which appears as a contribution from the lower bound state, the upper bound state, the resonance, and the anti-resonance added together, in which here lambda is just essentially a reparameterization of the energy eigenvalue. Then, to analyze the behavior near the exceptional point, we can show that it influences the dynamics, particularly on an early intermediate time scale. And to show this, we can apply these Puiseux-like expansions for these values here. In particular, we notice the norm. Notice the norm has a diverging term, that is G, the parameter that goes to 0 appears in the denominator. However, when we apply this in the survival amplitude, we find that the diverging contributions all cancel out. And so then, as a result, during this time scale given here, we can show that the survival amplitude takes this form with the characteristic t to the 3/2 term. And this term can be understood as appearing due to the combination of two factors. So the first factor is just a t squared e to the 2it, which is exactly what you would expect from a triple pole appearing in the integration for the survival amplitude from the effective EP3 behavior of the anomalous exceptional point. However, that's also modified by a term 1/√t, which comes from the direct influence of the continuum threshold. And that behavior is explored more in these two papers. Now, we can see this precise behavior against the numerical integration for the survival probability. The numerical integration is the dark curve, and then the dash curve is the 1 minus t to the 3/2 character, which we notice this 1 minus t to the 3/2 dynamics. It describes the survival probability on the time scale during which most of the decay occurs. This is then followed by a kind of oscillatory phase in which the dynamics can be described as a combination of these three terms, which are from a pole from the bound state, a pole from the resonance, as well as a inverse power law due to the long time tail. And so then the cross terms from these three terms all have an oscillation that is proportional to g to the 4/3. And so that's the frequency that appears here. And finally, in the asymptotic limit, t goes to infinity, the pole from the bound state then just gives us that the asymptotic survival probability approaches 4/9. So in this talk, I introduced a classification scheme for the simplest case of the EP2s. Then we introduced this anomalous exceptional point at the continuum threshold. For a general 1D model, I claim that these two conditions are required to observe the anomalous exceptional point. Mathematically speaking, the anomalous exceptional point is actually it's technically an EP2 plus a degeneracy. However, physically, it would act just like an EP3. Then we saw the time evolution in the threshold vicinity influenced by the EP, which has this 1 minus 2 to the 3/2 character. As a final comment, we propose the following general dynamical law for an EP near threshold. And the EP2 case is evaluated more carefully in this paper. Thank you.